Hello everyone. We are final year petroleum geoscience undergraduate student from University Technology Petronas would like to present the outcome of our study on identification of hydrocarbon using Lambda-Rho and Mu-Rho in Reservoir X under supervision of Dr. Maman.
Hello everyone, my name is Thenesh Sevoo.
And my name is Kuganesh Kumar, a final year petroleum geoscience student.
Hi, I'm Jeyehnderen Senderasegar. Let me start with the outline of this assignment. This assignment as usual start with the introduction, then follows by the theory and background of study, then objective and scope of study, background of study, project workflow and methodology, and then expected results and discussion, and then the success story of Lambda-Rho and Mu-Rho analysis, and finally the conclusion and future study. Let's move on to the introduction. This study seeks to demonstrate conventional approach of simultaneous inversion to enhance the hydrocarbon prediction and minimize the exploration risk. This study has two problem statements. The first one is feasibility of simultaneous inversion, where trend from the imposed model could be overinterpreted rather than the seismic data, and the second one is poor seismic data quality at deeper regions might affect the outcome. The objective of this assignment is to study the application of simultaneous inversion technique in determining the lithology and mapping the hydrocarbon distribution on a reservoir, and to evaluate the feasibility of Lambda-Rho versus Mu-Rho elastic parameter analysis in delineating hydrocarbon potential of a reservoir. Theory and background of study. Inversion is a technique to convert interface property to layer property with well logs as control. The outcome is P impedance, S impedance, and density. Lambda-Rho and Mu-Rho volumes are the product of subtraction and multiplication of the impedance volume generated initially. Crossplot between Lambda-Rho and Mu-Rho aid in detecting anomalies that can be interpreted as fluid or lithologies.
So talking about the workflow of the project, we will be starting with loading and quality controlling the well log data by removing any spikes and identify any anomalies present on the seismic data. Next, we will move on to the well log analysis to identify the zone of interest, followed by Gasman fluid substitution modeling to model different fluid scenarios. Next, feasibility study will be made on the well logs to identify the effectiveness of Mu-Rho and Lambda-Rho elastic parameters on distinguishing lithology and fluid distribution. Then, seismic to well tie will be made to match the well data to seismic data in time domain, and once the seismic to well tie process is complete, horizon interpretation can be made on the target interval. As a first step of the simultaneous inversion, low frequency model needed to be generated, and then we need to run the simultaneous inversion algorithm to generate P impedance, S impedance, and density cube. From these cube, we need to compute the Lambda-Rho and Mu-Rho volume and further analyze the relationship between these attributes in mapping the hydrocarbon distribution on a reservoir. Next, moving on into the methodology part, we will be first looking into the well feasibility study. In order to determine the feasibility of the simultaneous inversion method, cross-plot technique will be applied on each well, especially on Lambda-Rho and Mu-Rho elastic parameters before moving on into the full inversion workflow. Fluid replacement modeling can be made for different fluid phase composition and generate new elastic and density logs. We can generate P wave impedance, S wave impedance, Lambda-Rho and Mu-Rho using the existing P wave velocity, S wave velocity, and density logs. And for pre-inversion analysis, crossplot will be made to aid the lithofluid discrimination using the well log data. Figure on the right shows the crossplot between Lambda-Rho against Mu-Rho, which can be further classified into two different groups, inferred to be as gas sand and brine sand, further confirmed by the lowest density value. From these well log analysis, we expect reservoir sandstone to have low lambda value and high mu value. Seismic to well tie process is important to tie the well data to the seismic so that we can locate the actual location of the horizon of interest. The next step is wavelet extraction, and on a pre-stack data, we can expect the seismic data to experience a continuous loss of high frequency energy from near to far offset, and each CDP gather will be represented by different wavelets. We can study which type of wavelet in between the statistical or wavelet extracted from the well log can yield a better correlation and a better inversion result. The next step is to create a synthetic seismogram using the sonic and density log, and depth to time conversion can be made using the checkshot data to tie the well data to the seismic. Once seismic to well tie process is completed, horizon interpretation should be made on the target reservoir zone, which are often indicated by low gamma ray value, high resistivity, low water saturation, and a crossover between density and neutron porosity. Figure on the right shows the comparison between wavelets extracted at different angles and a well log analysis made on the well log to identify hydrocarbon zone. The next step would be to generate a low frequency model, where a low frequency model is an initial impedance volume built to represent the geological model of. The model is generated using the well log data such as P wave velocity, S wave velocity, density, angle gathers, and interpreted horizon. The values from the well logs are extrapolated using the log trend by interpreted horizons throughout the whole seismic volume to build the geological model. This method aids to integrate the information from several sources and compensate for missing information from seismic data by providing information, and improves the resolution and introduce the trends. The figure on the right shows the initial P impedance and S impedance low frequency model from one of the fields in Malay Basin. As a last step, we need to run the simultaneous inversion modeling. First, convolution process should be carried out to generate reflected P-wave synthetic trace by using Aki-Richards equation after wavelet extraction and generating low-frequency model. A simultaneous inversions algorithm, such as Hamilton-Russell's one, should be applied to the volume. As a product, three inverted volumes, namely inverted P impedance, inverted S impedance, and density, will be generated, and we need to quality check them by cross-plotting and comparing the result with the well data. Inversion workflow analysis can be continued with Lambda-Rho and Mu-Rho analysis by transforming the inverted P impedance, S impedance, and density volume into Lambda-Rho and Mu-Rho volume. Later, the relationship between these elastic parameters can be analyzed to enhance the hydrocarbon prediction. The figure shows the inversion model of inverted acoustic impedance, shear impedance, ratio of VP/Vs, Lambda-Rho, and Mu-Rho volume from Malay Basin. The detailed explanation on interpreting these volumes will be made in the next part.
Hello everyone, I'm Thenesh Sevoo, and I'll be discussing on the expected results and discussion part of this project. Also, I would like to recall our project objective, which is to evaluate the feasibility of Lambda-Rho and Mu-Rho elastic parameters in delineating the hydrocarbon potential of a reservoir by the application of simultaneous inversion. So this discussion part encompasses the inversion model, horizon slicing interpretation, and the cross-plot analysis. So for the inversion model, Lambda-Rho and Mu-Rho analysis are initially proposed as the lame parameters and core parameters, which are lambda and mu, who are the lame parameters, while the density is the core parameter. So these lame parameters are part of the P wave and S wave equations, velocity equations, where Lambda-Rho and Mu-Rho volume are the product of subtraction and multiplication of the impedance volume generated earlier. And bear in mind that impedance volume need to be converted to Lame's parameter volumes to compute other geophysical parameters that might aid in distinguishing the lithology and fluid. So for the figure showing Lambda-Rho volume and Mu-Rho volume of the Amangi hydrocarbon field, where the low Lambda-Rho values can be seen along the well trend, which indicating the presence of gas filled sands which are high porosity. The blue color shows the gas, which is the low Lambda-Rho values. While for the Mu-Rho volume, the large Mu-Rho volumes along the trend showing the high rigid faces which are consistent with sandstone, with the presence of quartz mineral, for example. So the faces should exhibit both high Mu-Rho value and low Lambda-Rho value as expected, and the target points should satisfy both of these conditions in order to delineate hydrocarbon potential of the reservoir. Next, we'll be discussing on the Lambda-Rho Mu-Rho interpretation from the horizon slicing. Okay, the data slice showing the distribution of elastic properties which are Lambda-Rho and Mu-Rho across the survey area, and this can be generated by combining the inversion results from the respective wells. And the diagram shows the Lambda-Rho volume and Mu-Rho volume of the Amangi hydrocarbon field, which shows the similar trend where low Lambda-Rho value and high Mu-Rho value indicates the hydrocarbon potential zone. And similarly, for example, the presence of silty sand represented by the low Lambda-Rho value and high Mu-Rho value indicating the zone of interest of hydrocarbon in field X of Malay Basin. lastly, we'll be discussing on the Lambda-Rho and Mu-Rho application in cross-plot analysis. Lambda is the measure of incompressibility, which is sensitive to the pore fluids, while mu is the representative of rigidity, where it's sensitive to the rock matrix. Both of these attributes are highly related to density, but in reality it's actually impossible to extract them from the seismic without being affected by density, and therefore in order to minimize the effect of density, the cross plot is constructed by using Lambda-Rho and Mu-Rho instead of lambda and mu alone. Ladies and gentlemen, a cross plot of Lambda-Rho and Mu-Rho, which is the incompressibility modulus and rigidity modulus, gives us a very good discrimination in pore fluid and lithology. For example, as we consider SP, density, porosity, and resistivity as attributes, they can help us to define the brine sand and shale zone, also in terms of the density increases towards the shale zone, while the porosity increases towards the hydrocarbon bearing zone, as well as the high resistivity value cluster, which is visible, that notices the hydrocarbon bearing zone. Therefore, Lambda-Rho and Mu-Rho gives us a more sensitive data that helps us to discriminate both fluid and lithology. Similarly, for example, the presence of gas in a sandstone, which we call as gas sand, causes the significant decrease in the compressibility, since gas is very compressible. Usually sand has higher rigidity, and gas in the sand does not really affect the rigidity, and therefore we can classify the region to have a low Lambda-Rho and a high Mu-Rho to be a gas sand zone. Therefore, this Lambda-Rho and Mu-Rho elastic parameters helps us to identify and delineate the hydrocarbon potential reservoir, which improves our interpretation as well as reduces our uncertainty in describing the reservoir.
Let's move on to the success story of the Lambda-Rho versus Mu-Rho. The first application applied for this is the application of simultaneous inversion and cross-plotting of rock properties for fluid and lithology discrimination in Niger Delta oil field. The findings from this application is that the Lambda-Mu-Rho technique was able to identify gas sand because of the separation in responses of both Lambda-Rho and Mu-Rho sectors. The first picture is the plot of Mu-Rho versus Lambda-Rho, showing sand and shale lithologies and the variation in the sandstone reservoirs based on dissimilar fluid content. And the second picture shows the inverted volume of far angle seismic stack for Lambda-Rho. The second application applied is the application of simultaneous inversion method to predict the lithology and fluid distribution in X field of Malay Basin. And the findings from this application is anomalous region represents the zone of interest is created through the Lambda-Rho versus Mu-Rho cross plot, and the Lambda-Rho volume shows the distribution of pore fluid. The first picture is the Lambda-Rho versus Mu-Rho cross plot with the anomalous region, and the second picture is the Lambda-Rho volume.
Okay, as a conclusion, simultaneous seismic inversion is indeed a powerful tool in predicting the lithology and fluid distribution, which improves the resolution and allows the characteristics of the reservoir better in comparison to the post-stack inversions. Besides that, feasibility of Lambda-Rho and Mu-Rho analysis onto the inversion volumes were proven in predicting the hydrocarbon and aids in better reservoir characterization. And we also like to propose to extend the study to understand the elastic impedance inversion, which is also angle dependent inversion that is generally sensitive to both fluid types and porosity, to assist the simultaneous inversion even better in future.
And these are the list of references that we use to complete this assignment.
And that's all from us. Thank you for watching and see you again.